Hi, I'm Dr. Kyle Gears, and this is another episode of Thursday Brain Bites. So in the last episodes, we were talking about the viscoelastic properties of the brain and how interactions between the cellular tissue and the CSF fluid combine to create a frequency-dependent stiffness of brain tissue. This week, we'll be talking about how people or scientists can take advantage of these frequency-dependent properties to reduce tissue compression and reduce cellular damage during insertion. So relating to this is a first study from Obaid and colleagues in 2022. They performed two insertions, one in ex vivo tissue, where you can see that there's an initial ramp up in overall force, followed by the puncture, and then an increasing force on the probe as it goes through the tissue. This is due to an increase in frictional forces between the electrode shank and the increasing surface area of the electrode arrays. However, when they repeated these experiments in vivo, they see the same puncture forces. However, you do not see the increasing frictional forces with the brain. So this suggests that in vivo, the interactions between CSF and tissue actually reduce the overall friction over long-term insertion, and we need to focus our abilities on minimizing puncture forces. Related to that, a study by Bjornsson et al. In 2006 looked at the effects of insertion speed in rodent brains and tissue compression and overall damage of the vasculature. What they were able to show is that during slow insertions, you see large amounts of tissue compression, and this can damage the tissue around the electrode sites. So moving to kind of a larger scale are studies using Blackrock Utah arrays by Norman and colleagues. So they came up with a pneumatic inserter, and in this case, they use a 1.75 gram weight to produce pneumatically actuated energy to drive electrodes into place. What they found is that by driving these electrodes into the target tissue at roughly 8 millimeters per second, they're able to fully insert the electrode because the tissue doesn't compress at high insertion velocities. So during high-speed insertion, you see that tissue does not compress, and then you have full insertion of your electrodes. However, a follow-on study by House and colleagues showed that distal to the electrode insertion sites, you can generate bleeding. And so this is due to traveling waves within the tissue that can cause damage distal to the electrode shanks. So at this point, we know that the brain has frequency-dependent stiffness characteristics. We know that increasing insertion velocity can decrease overall insertion force. However, large amplitude, high speed insertions can cause damage distal to your insertion site. So this leads us to the idea of vibrated insertion. So if we can use ultrasonic actuation to move the electrodes a small amount at a very high frequency, we can reduce the overall insertion force without creating these large volume damages. So this has been done by several colleagues, the most recent by Chen et al. In 2022, where they applied piezoceramic elements to silicon shank electrodes. And what they were able to show is that through vibration in the hundreds of kilohertz range, they can reduce the overall insertion force and subsequent tissue damage associated with the insertion process. This reduction in insertion force reduces the gliosis around your electrode shanks and provides better electrophysiological responses in the long term. I'm again Dr. Kyle Gears, and this has been another episode of Thursday Brain Bites.